Now let's see about full wave rectifier. A full wave rectifier does not block negative swings in the input voltage. Rather, it transforms them into positive swings as the output. One pair D1 round out of D2 allow current flow during the positive half cycle of Vin, while the other pair D3 round out through D4 allows current flow during the negative half cycle of Vn. Out voltage peak is 1.4 volt below the input voltage peak because the current passes through two diodes. The out frequency is twice the input frequency because in one full cycle we get two pulses. So if you have a 50 Hz, so times of that input frequencies. So the rectification process can be improved by using full wave rectifier circuit. Full wave rectifier produce greater DC output. As you see in the previous half wave rectifier, our VDC is 0.318 of VA. During full wave, VDC becomes 0.636 of VA. So it has two types of full wave rectifier. One, bridge network or four diodes configuration. Another, center tap transformer type of full wave rectifier. Let's start with bridge type of full wave rectifier. The DC level obtained from sinusoidal input can be improved 100% using a process called full wave rectification. The most familiar network for performing such function appears in this feature with its four diodes in a bridge configuration type. So during the period of T0 up to half of T over 2, that means from 0 up to pi, the part of the input shown in the feature, the feature 2.54, the resulting parts across the ideal diode are also shown in the feature 2.4 to reveal that D2 and D3 are conducting. Both these diodes are conducting, whereas D1 and D4 are in off state. Now let's see one by one. So in our circuit, we have four diode configurations, and also we have a transformer. This transformer, as you know, for step down type using. Also, we have a source 120 voltage supply, that means 120 VRMS. So with a 50 hertz. So during positive type in half wave from 0 to pi, which diodes are conductors? Let's see. So during the positive upper side, from this upper side, during the positive cycle, which diodes are conductors? Look, the current flows from positive to the negative, from high potential to negative. So when reaching our current here, we cannot pass through D1, but pass through D2. D2 is conducted. And current again pass through this resistor and round out through D4. So this is one pulse we can get during the positive. From 0 up to pi, we get one pulse from 0 up to pi. So which diodes are conduct? D2 and D4 are conducted. Again, during this negative cycle, from pi up to 2 pi, which diodes are conducted? So that means the upper side is a negative polarity and the bottom side is positive polarity. So the current passes from positive to the negative, from high potential to low potential. Then the current passes through D3, again pass through our load, again round back to D1. So that means from pi to 2 pi, D3 and D1 are conducted. So by this principle, we continue our results. So we can get in this V out becomes V maximum sine of omega t. So V out is a VDC or V average. So our VDC we can analyze from these results. So V average equal to VDC. That means area under the curve over base. So this means under full cycle we get two pulses. So simply obviously in the half wave we can done also in during this full wave, but in during full wave we get two pulses. So simply to analyze 0 up to pi integration of 0 to pi v out of d omega of t over the pi. It's simple, we can get our result. So this means integration of 0 up to pi v out means v maxima sine of omega t d of omega t over pi. So we can have the constant value Vm over pi integration from 0 up to pi sine omega of t d of omega of t. So integration of sine of omega t, we get Vm over pi, that is minus cos omega t from 0 up to pi. So this means cos of pi minus of cos of 0, that is minus of minus 1, again minus of 1, 1, 1 plus 1, 2. So our Vm over pi multiplied with 2. So our Z 2 Vm over pi. This means when 2 divided 2 pi, 0.636 of V max. This is our VDC or V average. And get V average these results. So the net result configuration of each 2.5 with its indicated current and polarity across R, since the diode as ideal. Let's see, our diodes are ideal. The load voltage is V out equal to Vi, as shown in the same figure. So from this positive cycle, that we can conduct D2, but D3 is open, our current pass through the load resistor and round out through D4. For the negative region of the input, the conducting diode are D1 and D4, resulting in the configuration of each 256. This feature. The important is that the polarity across the load resistor is the same as in feature 254. As the previous feature establishes the second positive factor as shown in the feature 56. Over one full cycle, the input and output voltage will appear as shown. So from the second negative type, from this negative, we conduct this D3 against the our load and back to the D1 conducted. So again the second pulse we get. So for one full cycle we get two pulses. Since the area above the axis for one full cycle is now twice that obtained for half-wave system, the DC level has also been doubled. So what is the analysis? You can simply 2 times of half of wave rectifier that we can get 0.636 of V maximum during full wave rectifier. If silicon rather than ideal diode are employed, as shown 2.58, the application of which voltage are around. So you can minus from our V maximum if you use practical diode are using. So our VDC becomes 0.636 of Vm minus of to nil voltage or voltage drop of Z diodes. Then again, if V maximum is sufficiently greater than 2 voltage of nil, that means V diode, then equation 2.10 is often applied as the first application for VDC. So peak inverse voltage, the required peak inverse voltage of each diode ideal can be determined from figure 259 obtained as the peak of the positive region of the input signal for indicating loop the maximum voltage across R is Vmax and the PI rating is definite. So peak inverse voltage during full wave rectifier is approximately equal to V maximum or V are equal to V maximum during full wave bridge rectifier. So this is about bridge type full wave rectifier. Now let's do one example. From the given of this circuit, we have 120 voltage supply. That means 120 VRMS, and our transformer is 4:1. That is step down transformer. So let's determine V out, or that means let's determine our VDC, ideally and practically. Let's now analyze. So first, the given value V source 120 VRMS and frequency in 50 Hz. Transformer ratio 4:1. So that means step down. So let's find first V peak. V peak becomes root 2 times of VRMS. Then root 2 times 120. That becomes, let's calculate it, 120 times root 2. Approximately 170 V peak. Now, what about secondary voltage? This is primary input voltage. So V primary over V secondary equal to N1 number of turn ratio over number of ratio 2 secondary winding. So this becomes 170 over Vs equal to 1.5. Let's cross. V secondary becomes 170 over 5. This becomes 34. V maximum of secondary voltage. Now, VDC is equal to 0.636 of V maximum. So first check find ideal diode by using ideal diode. when using idle diode, that is perfect conductor and also perfect insulator. So VDC, we can use VM directly, 0.636 times 34. Our VM of in secondary is 34. So this becomes 34 times 0.636, 21.6 volt VDC. When practical diode, when using practical is one for silicon type, our VDC becomes 0.636 of V maximum minus 2 of VD, because the current pass through two diodes. So 0.636 34 minus 1.4. The result is calculated 34 minus 1.4, 30.6, 0.636 times 36. The result becomes 20.7 of VDC during practical. So we can get also IDC. IDC equal to VDC over R. Again, VRM is during full wave rectifier, V maximum over root 2, handled by this one. So during full wave, we get 20.7. If you see in the previous, during half wave, we get 10.5, approximately like that. So when using full wave rectifier, it's improved 100% than half wave rectifier. So during half wave, it blocked 50%. So our result is almost 40.6 or like that, or 50% results. But during full wave result, it's improved more efficient than half. Now let's see the second type of full wave rectifier, that is center tapped transformer. A second popular full wave rectifier appears in the figure 2.60 with only two diodes, but requiring a center tapped transformer to establish the input signal across each section of the secondary of the transformer. During the positive portion of Vi applied to the primary of the transformer, the network will appear as shown in the figure 261, with positive pairs across each section of the secondary coil. D1 assumes the short circuit equivalent and D2 the open circuit equivalent, as determined by the secondary voltage and the resulting current direction. The output voltage appears as shown in the figure 6.1. So during that positive, only the upper side of the secondary transformer conducts. That means D1 also conducts. So we get one pulses. But the second type of diode is, or D2 is, open during this time. During the negative portion of the input, the network appears as shown in the figure 2.6.2, reversing the role of the diode but maintaining the same polarity for the voltage across the load resistor R. The net effect is the same output as the appearing in the figure 5, or that is the previous what we see, with the same DC level. So for this input signal, that is a negative cycle from pi to 2 pi, that the bottom side of our secondary transformer is functional. That means D2 is conducted, but D1 is open. So we get another second pulses. So by this principle, from center tap transformer, we have get a full wave rectifier. Another difference between center tapped and bridge type full wave rectifier is the peak inverse voltage. During the center tap type, the peak inverse voltage, the network in the figure 2.63, as is seen, will help us to determine the net PIV peak inverse voltage for each diode for this full wave rectifier, inserting the maximum voltage for the secondary voltage and the maximum voltage as established by adjoining loop results in the circuit. So during center tap transformer, PIV is equal to V secondary plus voltage in the resistor. So that means V maximum plus V maximum, we can get 2 times of V maximum. So PIV greater or equal to 2 of Vm during center tap transformer full wave rectifier. So in general, when you summarize it of rectifier circuit, we have three types of rectifier circuit. One of the half wave rectifier. So during ideally, when our diode is assuming as an ideal, only direct VDC becomes 0.318 of Vm, but practically, so when our diode is a silicon type, so our VDC becomes 0.318 of Vm minus 0.7. During full wave 1 bridge rectifier, during ideal diode, VDC becomes 0.636 of Vm, but practically our current passes through two diodes, so our VDC becomes 0.636 of Vm minus 2 times of Vd. During center tap transformer, our current from passes through one diode, so our VDC during ideal 0.636 of Vm by ideal diode, but during practically the current passes through one diode, so minus 0.0 of Vm. So our VDC becomes 0.636 of Vm minus 0. So Vm means peak of the AC voltage. So in the center transformer circuit, the peak AC voltage is the transformer second barrel to the tappers. This is all about today's class about rectifier circuits. If you have any question, you can put on a comment box. Thank you for your attention.